Thanks very much, Maria Rosario, and thank you to the organisers for the invitation to be part of this workshop. So as Simon's said already, this talk is a kind of part two of his presentation, focusing on the implementation of our numerical method for scattering by fractal structures. The work I'm going to talk about is somehow independent in the sense that it stands alone as just a question of how do you do integrals of singular functions over fractals. So it's joint work with Andrea Moyola, my postdoc Andrew Gibbs, and our undergraduate student Botond Major. But it's strongly influenced by the collaboration with Simon and our team working on scattering problems. Okay. So overview of the talk, the aim is to derive and analyze quadrature rules for singular integrals on fractal sets. Maybe I should sort of, just to remind us, if you never did a course in numerical analysis, then maybe you've never thought about this. But yeah, basic ideas in numerical analysis to do with quadrature. Typically, you encounter integrals on the real line, and you have some function that you want to find the area under the graph. And typical techniques in numerical methods would involve discretizing the integration range, so perhaps splitting it up into some mesh, and then on each mesh element doing some sort of approximation to the function, perhaps a polynomial interpolant, and then you integrate the polynomial interpolant. For instance, you might just do something like a midpoint rule, like this, and you approximate the integral of the function by the area of these rectangles. Okay, it's a sort of composite midpoint rule for a one-dimensional integral. This works well when the integrand is smooth. When the integrand has a singularity, you have to work a bit harder. So say if I'm integrating from 0 to 1, and I have a function which blows up at the origin. For instance, f of x equals x to the minus half or something like this. This is still integrable, but this kind of technique won't give you a very accurate answer. And typically then what people do is apply some sort of mesh refinement scheme. So over here the function's smooth, so you can do a standard mesh. But close to the singularity, maybe you have to do some finer mesh in order to keep good convergence properties and good accuracy. So this is this kind of standard way of approaching this kind of integration. But actually there are other ways which generalize quite nicely to these fractal sets. And they involve recognizing that this interval 0, 1 is actually self-similar and you can break it into two pieces. And they're both similar to the original integral. And turns out you can write integrals like this over this interval, which is a singular integral. You can write it in terms of a regular integral over this portion, okay, by a change of variable and a rescaling. And that's the technique that I'm going to talk about in this context, this broader context of integration on fractals, but very much with this background in mind.
So in other words, you just cut off the singularity?
Yes, there's a way you can cut off the singularity, but I'll explain it in this more general setting. Okay. So motivation, we've already heard from Simon, these scattering problems, and these are actually some solutions, scattered fields of the problem that Simon was talking about, and I'll say a bit more about that later. But I'm going to keep things very simple in this talk and just look at a model problem which is evaluating this integral. It's a double integral with respect to Hausdorff measure over some fractal set gamma of this kernel 1 over modulus x minus y. Okay. And this is the kernel that would arise if we were looking at the Laplace problem that was discussed at the end of the last talk. This could be replaced by the Helmholtz kernel in the application. Okay. And I'm going to keep things very simple deliberately so that it's easy to follow, but we've considered other types of singularities, so other algebraic powers here, but also logarithmic singularities. And we've also considered more general measures, so self-similar measures on IFS attractors, but I'm just going to present for the Hausdorff measure. Okay, so this audience knows about fractals, so I'll skip this very quickly, but from the scattering point of view, there are many interesting scattering problems involving fractal structures. Somebody mentioned broccoli yesterday. Here's my broccoli picture. If you ever wanted to know about acoustic scattering by broccoli, we're the people to ask. But specifically, so I've done work in the past relating to, and Simon has too, relating to urban noise propagation. So you might be interested in how traffic noise interacts with vegetation, for instance. I have a collaboration with the UK Met Office who are interested in electromagnetic scattering by ice crystals and aggregates of ice crystals, which often have a fractal structure. And also there's been a lot of work in, as this community knows, about antennas in mobile communications using fractal structures. Okay. Mathematically, of course, we understand fractals, not so simple to give a definition of, but roughly speaking, they have structure on every length scale, some sort of self-similarity, some non-integer dimension, and a definition involving recursion. And like Simon, I'm going to focus on the special case of attractors of iterated function systems, which have this property that they're equal to the union of a finite number of scaled copies of themselves. Okay. So this is the same definition that Simon showed, except I'm being a little bit more specific here. So in this case, setting of Rn, I've got a collection of contracting similarities, and in that setting, you can write each contracting similarity as a composition of a multiplication by an orthogonal matrix AM, some scale factor rho m, which should be between 0 and 1, and then a translation vector delta m. Okay. So they always have this same form, and this is how we'd specify the mappings in the IFS. And then the attractor is the unique non-empty compact set that is invariant under this map, and it can be recovered as a limit of this fixed point iteration by this map. And Cantor's set is the simple example. Okay, and of course there are other examples, as Simon's mentioned. Cantor dust, the Sierpinski gasket or triangle, Sierpinski carpet, Koch snowflake, and here is an inhomogeneous example. So it's a sort of modified version of this Cantor dust, where the scale factors are not the same in each of the cases, and one of the components has a rotation in it, so that you break the symmetry of the set. And we can handle all these cases. Okay, Simon already reminded us that the definition of this Hausdorff measure, but here it is again. So a Hausdorff measure of a subset given by this lim inf over coverings of the set by sets ui with diameter less than delta, and we're looking at the sum raised to the power d. And then we define the Hausdorff dimension as this infimum of all the d prime, such that hd prime of e is 0. So there's this point at which the measure drops from infinity down to 0, and that's the dimension of the set. Okay, and as Simon's already mentioned, for IFS attractors satisfying the OSC, that's the case we're considering, this dimension agrees with the similarity dimension. So, for instance, log 2 over log 3 for Cantor's set, and more generally with this framework of IFS here, the dimension solves this equation that Simon already showed. Okay, for the purpose of this talk, we're really going to now start using some of the properties of these measures, and a key property is this scaling property, okay, which is a generalization of what we see for Lebesgue measure on Rn. So if the dimension of the set is d, and we look at the Hausdorff d measure, if we scale the set by a factor rho, then the measure gets scaled by rho to the power d. And this is what we're used to for 1D integrals. Length gets scaled by rho. If we're looking at 2D integrals, area gets scaled by rho squared, and so on. And this measure is proportional to the Lebesgue surface measure when d is an integer, and gamma is some simple shape like a line or an area or a volume. As Simon already mentioned this in the context of a boundary of Lipschitz open set. Okay, so that's the setup, and so some examples here. Simon already talked about some of these, but here's an example in 3 dimensions. So this is a Sierpinski tetrahedron, and there's 2 versions here. One is disjoint with a scale factor, gives a dimension of 1.41. This is the non-disjoint one, which touches at the vertices, and that has dimension 2. Okay, so that's just a basic setup. What about this quadrature problem then? So I said we want to try and study quadrature rules for this double singular integral. And this arises in integral equation formulations of elliptic PDEs on domains with fractal boundary, as Simon's mentioned. And to motivate our methods, I'm going to first consider the sort of analog of this situation here, where we have a smooth integral, it's a smooth integrand, and just a one-dimensional integral, and then we'll go to the double integral case. And I should say that in special cases, so for instance, if gamma is a Cantor set in R, then there are very good quadrature rules for this problem. And so Gauss rules are available, and Giorgio, who's in the audience, has worked on this problem. And we've implemented those rules, and they're very, very effective. But we've also studied a more general, less accurate approach, which is analogous to this composite midpoint rule, and it works for pretty much any attractor, but it's a lower order approximation. But that's been enough for our purposes. So the picture is just as I sketched over here. We're going to apply a composite midpoint rule or barycenter rule, and the basic idea is that you take your integration domain, you decompose it into subsets with maximum diameter less than some number h, and then on each you split your integral with respect to whatever measure you're working as a sum of integrals over the sub-elements, and then each one you approximate by a simple one-point quadrature rule. Okay, so it just takes the value of the function at some point in this interval gamma j, and multiplies by the measure of that set, and that's what we call our quadrature rule, QH. Okay, and this is a sketch in the 1D case where integration is over an interval. This is a sketch in the 2D case where integration is over this domain here. Just take some subdivision and choose some points inside the elements. If you choose the points to be the midpoint, or more generally the barycenter with respect to the measure mu, then you have this nice property that the quadrature rule is exact, not just for constant f, but also for linear f. And that means that just by a standard Taylor series argument, you can show that the error in the quadrature rule is big O of h squared as h tends to 0 for smooth functions f. Okay. So that's the setup we're going to be using in this context of IFS attractors. And as Simon's already mentioned, these IFS attractors have a nice structure that you can exploit to mesh them. Simon was talking about meshes for solving the integral equation. Here I'm talking about the same kinds of meshes, but for doing quadrature. Okay. So this is the setup that I had before with my similarities, and there's this sort of standard notation where gamma m with a vector index m just indexes one of these components of the set. So here's some examples. For the Cantor dust, I've got gamma 1, gamma 2, gamma 3, gamma 4 at the top level. Then at the next level down, I might have, say, gamma 2, 1, gamma 2, 3. And then this is gamma 1, 1, 1, where I've applied the first contraction 3 times. Okay. And you can use that to mesh your attractor. And so here for the Cantor dust is an example with level 1. We have 4 elements. Each element is a fractal. This is level 2, so it'd have 16 elements. Each one is a fractal. And level 3, I'd have 64 elements, and so on. Okay. And the idea is that the finer the mesh, the more accurate the solution because of this h squared accuracy down here. Okay. So that works fine when you're in a homogeneous case, but when the contraction factors aren't all equal, you end up with meshes that aren't quasi-uniform, and so it's natural to consider the quasi-uniform version of this. So that's where you don't refine down to the same number of levels everywhere. You do a local strategy that just looks at the size of the elements, and you choose a different index set. So you look at all the vector indices for which the components have diameter less than or equal to h, and the diameter of the parent is bigger than h. Okay, and that for the Cox snowflake, this is the version that you get by just going down level by level. You see that there are some big elements in the middle, small elements around the edge, so it's not quasi-uniform in the limit. But this is the version, the LH version, where you just fix h and just choose the elements of diameter approximately h. And this is a quasi-uniform version. Okay, so then we apply this barycenter rule. As I said before, approximate the integral by the sum of the measures of the components multiplied by the function evaluations at the nodes. And then the weights can be computed because this scaling property of the measure tells me that the weight of the component is the measure of the original set multiplied by this product of contraction factors. And the nodes are the barycenters, and these are defined in terms of this integral, but actually what's nice is that you can evaluate these exactly in terms of the parameters of the IFS, so you can find those. And then we have this order h squared error if f is smooth in some suitable neighborhood of the attractor.
So how is the C2 with respect to?
Yeah, so that's a good question. So you have to remember that so for this Cantor dust example, the barycenters are actually not in the set. The barycenter is like a midpoint of a component here. So you need the function to be smooth, sort of outside.
So you consider this as a function of R2?
Exactly, yeah, or some subset of R2. That's right. But that's completely reasonable for our application, where it comes from some function that's defined globally. Okay, and this, yeah, I won't say anything about that. Okay, we wanted to talk about singular integrals. So this double integral, and the basic idea is to use this composite barycenter rule in combination with the self-similarity of the set. Okay, so we're going to use the self-similar structure of gamma, and also the homogeneity of this kernel. So this kernel behaves nicely under similarities. And in particular, if I scale both x and y by the same number rho, then this kernel scales by 1 over rho. Okay, I can take it outside the integral. And this is going to allow us, as I was sort of suggesting rather cryptically over here, allow us to write singular integrals in terms of regular integrals by exploiting this. Okay, and this is presented in these two papers, which have come out recently. But these methods are not really new, so they've been known for a while, and there's some papers in the physics literature that are applying this, and Giorgio also used this kind of property for evaluating integrals of polynomials, because they have the same homogeneity kind of idea. But in our community, numerical analysis community, there's also this idea of hierarchical quadrature, which is an alternative to this mesh refinement strategy, which has actually been implemented and used in our community by these people here, Böhm-Hackbusch and Mesmer. Okay, but that's just for the case, not the non-fractal case. This is just for the case of an interval or a rectangle. Okay. So how does this work? So I'm going to try and illustrate this for a simple case of the Cantor dust. So I'm trying to do a double integral of this singular kernel over the Cantor dust. And I'm going to first of all decompose it, use this self-similarity, decompose gamma into 4 pieces. Gamma 1, gamma 2, gamma 3, gamma 4. And so then this double integral becomes 16 double integrals, okay, of the integral over all the possible pairs of these elements, okay. So I get 16 terms here. M is 4 in this example, but I'm writing it more generally. Some of them are singular because the interactions between gamma 1 and itself, or the interaction between gamma 2 and itself, these are singular. But the ones where m is not equal to n here, interaction between gamma 1 and gamma 2, because of the disjointness, there's a finite distance separation between these. This kernel is then smooth on that product, and therefore this is a regular integral. So some of these are bad, some of these are good. I'd like to deal with these bad ones here. And I can do that by, just in very simple terms, using this homogeneity and making a change of variable. It's not so hard to see that the integral over this gamma 1 with itself can be written in terms of the integral over the whole set against itself. Okay, so I can write this integral in turn as a product, proportional to this integral of the original integral over the whole set. And that's using the self-similarity of gamma and the scaling property of this measure. So the scaling property of the measure comes in with this rho m to the power 2d. Okay, the rho m to the d, that comes from this scaling property of the Hausdorff measure. The factor of 2 here comes from the fact that we're doing a double integral, not a single integral. And the rho m to the minus 1, that comes from this homogeneity. Okay, so when I rewrite this integral, I get a factor of rho to the minus 1. So basically just taking my double integral over gamma 1, zooming out, and writing it as a double integral over the whole set. And this is great because it means that these singular terms, I can substitute in this formula here, and gamma, it's I gamma gamma, this double integral is unknown, but the nice thing is I can move this then to the left-hand side and divide by the constant pre-multiplying it, and I get a representation formula for a singular integral in terms of regular integrals. Okay, magic. Yeah. So this is fantastic, and it works for this interval as well. Okay, so it's a super simple idea. Right, the integral over this singular bit can be written in terms of the original integral over the whole interval, and that allows you to write the singular integral in terms of an integral over this bit. Okay, and then the point is that you can use whatever quadrature rule you like for these regular integrals. So for instance, we could use this composite barycenter rule, and then we get order h squared error for the evaluation of this singular integral. Okay, provided that we've got this separation property, this disjointness. Okay, so that's the disjoint case, and that's what we studied first. But since then we've been looking at non-disjoint cases, and then it gets interesting. So if you try and do the same thing for this Sierpinski gasket, at the first level of decomposition, I've got these three elements, gamma 1, gamma 2, gamma 3. And the issue is that they touch at these points. Okay, so there's no longer this separation condition. So going back to the previous slide, some of these integrals here will no longer be regular. Okay, they'll have a singularity. In fact, they'll all have a singularity in this case. But it's somehow a weaker singularity. It's a point interaction rather than a sort of full singular interaction. So I'm going to use some compact notation just to make life easier. So I12 just means the double integral over gamma 1 times gamma 2, okay, and so on. And at level 1, we have this decomposition. So the integral over the whole fractal with itself is 3 times the integral over gamma 1 with itself. That's just by the symmetry of this situation. Plus 6 times this point interaction. Okay, and this number 6 comes from all the interaction of 1 with 2, 2 with 1, 1 with 3, 3 with 1, 2 with 3, and 3 with 2. 6 terms. Okay, but both of these are singular. Yeah. The first one, the I11, that can be written in terms of the original I gamma gamma, just like before. And then what about the second one? Well, the second one, we have to go down another level. So the interaction between 1 and 2, we can decompose that further. And we see that it's equal to this interaction between 1, 2 and 2, 1, plus a load of regular interactions, right, where there's a separation between the components, which are good. So all these guys here are nice. It's only this one that's not nice. But then I can play the same trick and write this interaction between 1, 2, and 2, 1 in terms of the interaction between 1 and 2. Just zoom out using this self-similarity. Okay, and I get some constant of proportionality. So that's great. What it means is that I can write down a linear system that's satisfied by these singular integrals. This is the self-interaction. This is the sort of point interaction between touching components. And the right-hand side is nice integrals that I can evaluate using a composite barycenter rule. These are all just numbers. I can solve the system to get the singular integrals in terms of regular integrals. And again, I get a nice error estimate on the quadrature rule. For the snowflake, things become a bit more interesting still. So I now get a linear system with 3 singular integrals as unknowns. The first one is the full singular interaction, double integral over the whole snowflake. This one, I12, this is the sort of edge interaction. Okay, so this is a double integral over gamma 1 cross gamma 2, and the singularity is on this Koch curve. And then the third one is I23, which has a point interaction just at this point here between 2 and 3. And again, the right-hand side is all stuff that I can evaluate accurately, and so I can evaluate this. Just to very briefly say something about extensions. So all of this is just a very simple special case. We can do singular integrals for certain singularity locations. We can do general power law kernels. We can do logarithmic kernels. Helmholtz kernels, like Simon was talking about via singularity subtraction, and more general self-similar measures on the attractor, where this Hausdorff measure is a special case. And if I can just have a couple of minutes to show you some numerical results to show that this really works. So this is a convergence plot of this is the relative error in the quadrature as a function of the number of quadrature points, increasing number of quadrature points for Cantor set with different contraction factors. And in each case, we get very close agreement with our order h² error. And then here are some results for a non-standard, so a self-similar measure on the Koch snowflake with randomly chosen weights. And again, we get a nice convergence. We did a comparison with some Monte Carlo approach. And then this is for the non-disjoint case. There's a lot of things here, but basically we get our, with this method, we get our order h² accuracy, even for these cases where we have non-disjointness, close agreement with the theory and the numerics. Okay, so partly we've addressed the issue that Simon was saying about the non-disjoint examples. This doesn't deal with the approximation theory, but it does deal with the quadrature side of things. Okay. And here are some plots of the scattered field for Simon's integral equation in the case of scattering by some fractal screens. And this is the tetrahedron in 3D. And yeah, I think I'll finish there with some references. Thank you.
Thank you. Are there questions?
Hello, thanks for the talk. Do you have any idea if this method or homotopy method could be used when you do not have exactly homotopy but inequalities? So that means if something which is refined is smaller than rho times the integral, the principal integral, or would that fail if you do that?
So I think it would fail, but there might be some sort of approximation that you could do. It might give
that would be the approximation I was thinking of, not the exact value, of course.
But we haven't looked into that. But yes, it could be. Yeah, and we're interested also in if you can ask if it's not a similarity, but it's some sort of affine map. Is it possible to say anything?
And double layer potential?
Yes. So we've been we've been thinking about other examples, but that's still work in progress. But yeah.
Thank you.
Other questions?
So it then follows that you get this h² convergence for any integrable singularity?
I mean, so what are the assumptions on
Yes,
singularity?
yes, exactly. Yeah, that's
So
right.
Any integrable. And what is H for Sierpinski gasket?
What is the H?
H, yeah.
So H is the mesh width. So for instance, so it's whatever you want it to be. But where's a picture? Yeah. So this is maybe the snowflake is the easiest thing to see. But you choose an H, and then you can generate a mesh with that H. H is the largest diameter of the elements.
So what H squared means? When you discretize
Okay.
an interval,
Yeah.
1 over n.
Yeah. Let me find my. So this is the slide. This is the slide I skipped over, and I shouldn't have skipped over. So you make a connection. So yeah. So in the homogeneous case, the number of quadrature points, you want to know how does this relate to computational cost, right? So it goes like h to the minus d, which is consistent with the standard setting. So if you're in 1D or 2D, then you have this same scaling. So it does depend. The number of quadrature points relates to h in a way that depends on the dimension, of course. Yes, the Hausdorff dimension. Yeah, in a way that's consistent with the usual setting.
Is there any analytical result for simplest sample so that you could control your numerical approach to cutoff singularity?
Any so
Maybe you have some analytical result for simplest fractal or set maybe to control your numerics.
okay, yeah. So our numerics we've been comparing to a sort of self-reference. We use a high order approximation as a reference. So yeah, we don't have an exact solution. If anybody knows any integral identities involving fractal measures and singular functions, I'd be very, very pleased to hear. But I don't know any.
So you use the barycenter approximation, but if you replace this by the integral average of the function value, then what happens? So you expect a similar result?
But that would be, you'd then have to know what that integral was, right?
Oh, I mean that using the Hausdorff measure, self-linear measure as a measure on the set.
Yeah.
In such case, you don't need the value. You only need the value on the fractals.
Okay.
Yeah, if you use the integral average.
Yes.
And
But how would you compute that average?
Sorry?
How would you compute that average?
Oh, it's just there is a measure, Hausdorff measure, and you will integrate the function over this small space.
Yeah.
And divided by the area,
Sure.
That's it.
But you have to actually compute it somehow, right?
Yeah, but in theoretically.
Okay.
Yeah. Theoretically, you can easily prove that those functions, discrete functions, will convergent to the original function in L2.
But if I knew how to integrate it, I wouldn't need a quadrature rule. So then I'd kind of...
Okay.
Other questions? Remarks? Okay, if not, oh yes, sorry.
So, how important are these point interactions? For example, if you do the focus, you take these triangles and you move them, so there is no intersection.
Yeah.
So will it be similar? So will you get some kind of convergence?
Yeah. So
you see, you just put some kind of step.
So in these results here, actually, I didn't have time to explain, but what I'm showing here is, so for this Sierpinski triangle, I'm showing two approaches. What's described as the old method is where you just deal with the self interactions and you ignore the point interactions. You pretend that they're regular and you just apply the barycenter rule. You don't treat them specially. The new method is where we solve this 2x2 linear system to find them. And you do see a difference in the convergence. So that the new method gives this order h² convergence. If you ignore them and you just treat them as if they're regular, then you only get order h convergence. So it does. You still have convergence, but in the same way that for yeah, in 1D, if you just integrate naively, you still get something, but it's not optimal.
Other questions?
I have a remark. That what Dave is doing is very important, also to answer your question. Once you go to find the divergence abscissa of those integrals, then the self-interactions are crucial. So it is important what Dave does.
I have a question, maybe I miss point. Are you taking into account when the kernel is weakly singular? So you consider singularity, non-singularity?
So I mean, when I say singular, I mean weakly singular.
Weakly singular.
Yeah.
So when the points are close.
Yes. So this kernel.
Yeah.
The double integral. This is weakly singular when t is less than d. The d in the d set.
Yes, but I mean that when you compute the quadrature formula, if x and y are very close but not so close, do you take into account that case?
So it's taken into account automatically because we write all of those cases in terms of integrals where there's a good separation between the. So we never actually integrate the weakly singular integral directly.
Okay.
We could. So an alternative strategy would be to do this kind of mesh refinement. Yeah. But we're avoiding that. And when I had a student do a comparison between just for a 1D integral, comparing this to this self-similarity, and this is just so much better. Because when it works fantastically because you completely move away from the singularity, and then you have very rapid convergence, especially if you can use Gauss rules. And
I see. Okay. Other questions, remarks? If not, let's thank the speaker again.